4 billion miles from where you're sitting, there is a small ball of ice that should, by every reasonable expectation, be one of the most boring places in the solar system. No weather worth mentioning, no internal engine, just rock and frozen gas, sitting in the dark, doing nothing. Except it isn't doing nothing. In June of 2025, a team of astronomers confirmed something about that little world that had been dismissed as a crazy idea less than a decade earlier. Pluto's upper atmosphere is roughly 30 degrees colder than physics alone can explain, and the reason is that a thin haze wrapped around the planet is functioning as an active cooling system, not metaphorically, measurably. Pluto, a dwarf planet with barely any atmosphere at all, appears to be running something astronomers are now calling a genuinely new kind of climate, one that doesn't resemble anything else we found anywhere else in the solar system. To understand how strange that actually is, you need to go back to how little we knew about this place for most of the last century. In 1930, a young astronomer named Clyde Tombaugh spent months at Lowell Observatory in Arizona comparing photographic plates of the night sky, hunting for a single point of light that moved against the fixed background of stars. He found it. That point became Pluto, and for 76 years afterward, it held its place as the 9th planet in every textbook. That changed in 2006, when the International Astronomical Union formally redefined what counts as a planet, and Pluto, unable to meet the new criteria around clearing its orbital neighborhood, was reclassified as a dwarf planet instead. It became, for a while, something of a punchline. What almost nobody expected was that the reclassification would coincide with the beginning of the most scientifically interesting chapter of Pluto's story, not the end of it. For most of the 20th century, Pluto was little more than a smudge, even through the best telescopes available. Astronomers couldn't measure its size with any real precision, couldn't resolve surface features, and had no confirmed evidence of an atmosphere at all. Everything written about Pluto before the space age was, in a real sense, an educated guess stacked on top of another educated guess. Some scale helps put the place in perspective. If Earth were shrunk down to the size of a basketball, Pluto, at the same scale, would be smaller than a golf ball, drifting roughly 40 times farther from the sun than Earth does. Sunlight out there is so weak that high noon on Pluto looks close to Earth's twilight. Surface temperatures hover around minus 380 degrees Fahrenheit, more than 250 degrees colder than the coldest temperature ever recorded anywhere on Earth's surface. At that temperature, nitrogen, the same gas that makes up most of the air in your lungs right now, freezes into a solid, the way water freezes into ice. None of that cold was on its own surprising. Scientists had done that math decades before any spacecraft got close. What turned out to be surprising is that Pluto is colder than even that. Extreme math predicted, by a wide enough margin, that something else had to be going on. Figuring out what took nearly a decade, two very different pieces of technology, and one scientist willing to propose an idea that most of his peers initially dismissed. The first real look came in July 2015, when NASA's New Horizons spacecraft, after a journey of almost 10 years, finally reached Pluto. It had exactly one pass to work with. There was no orbit, no second attempt. Traveling at more than 30,000 miles per hour, the spacecraft had only a narrow window to gather everything it possibly could before continuing on into deep space, never to return. What it sent back reshaped how scientists understood this world almost overnight. Dominating one hemisphere was a massive, pale, heart-shaped plane, later named Tombaugh Regio in honor of Pluto's discoverer, its surface strikingly smooth and young-looking compared to the older, heavily cratered terrain surrounding it. Nearby, mountains of water ice rose more than 10,000 feet, made of material that behaves less like the ice in your freezer and more like solid rock at Pluto's extreme temperatures, hard enough that striking it would produce something closer to a metallic ring than a crunch. And drifting above all of it, extending hundreds of miles into the sky, were distinct, layered bands of pale blue haze, visible even backlit by the distant sun. Nobody had expected a small, cold, effectively airless world to have anything resembling structured atmospheric layers at all. At the time, there was no way to know what that haze was actually doing. Was it inert, just sitting there? Or was it somehow connected to the puzzle of why Pluto ran colder than the models predicted? New Horizons couldn't answer that question. It had one look, and then it kept moving. Whatever the haze was doing would have to wait for an entirely different kind of instrument, one capable of studying Pluto's atmosphere from Earth's part of the solar system without ever sending another spacecraft anywhere near it. That instrument didn't exist yet in 2015. It would take the James Webb Space Telescope, launched in December 2021, to finally provide it. Webb doesn't work the way a flyby camera does. Rather than photographing a surface, its instruments read light itself, splitting it apart, the way a prism splits sunlight into a rainbow, and using the resulting spectrum to determine what an object is actually made of and how it's behaving thermally. Applied to a target 4 billion miles away, That's an extraordinarily precise kind of listening, translating faint infrared signals into detailed information about temperature, composition, and structure. There was a specific technical obstacle standing in the way, though, and it had blocked earlier attempts for years. Pluto and its largest moon, Charon, orbit so close together and appear so close together from Earth's perspective that separating their individual light signals had been effectively impossible for older telescopes. Astronomers trying to isolate Pluto's own thermal signature kept getting Charon's signal bleeding into the measurement, making a clean reading of Pluto's haze alone unattainable. That changed once Webb's mid-infrared instrument, known as MIRI, proved sharp enough to resolve the two bodies separately, something researchers achieved starting with observations in 2022. What that separation finally allowed scientists to test was an idea first proposed back in 2017 by Shi Zhang, a planetary scientist at the University of California, Santa Cruz. Zhang's proposal ran directly against the standard intuition about how atmospheric haze behaves. On most worlds, and in most textbook models, a hazy atmosphere works like a blanket, trapping heat near the surface the way greenhouse gases do on Earth. Zhang argued Pluto's haze was doing something closer to the opposite, absorbing weak sunlight during the day, then radiating that heat directly back out into space at night, fast enough that the haze itself functioned less like insulation and more like a radiator, actively bleeding heat away from an atmosphere that had very little heat to spare in the first place. Zhang himself has described the proposal, in his own words, as a crazy idea at the time, one that drew real skepticism from other researchers in the field, precisely because there was no way to test it with the instruments available in 2017. The test finally came from a team led by Tanguy Bertrand, an astronomer at the Paris Observatory, using Webb's newly separated thermal signals from Pluto and Charon. The results, published in Nature Astronomy in June 2025, confirmed Zhang's prediction directly. Pluto's haze does emit a detectable, significant thermal signature, consistent with exactly the cooling mechanism Zhang had proposed 8 years earlier. Bertrand has described the confirmation as genuinely satisfying for the team precisely because the original prediction had been considered a stretch by much of the field when it was first floated. The measured result showed Pluto's upper atmosphere running at roughly minus 333 degrees Fahrenheit, close to 30 degrees colder than earlier models, built without accounting for this haze mechanism, had predicted. Sit with that for a second, because it's a genuinely unusual finding in planetary science. Pluto isn't simply cold because it sits far from the sun. In a measurable, mechanistic sense, it is actively regulating its own atmospheric temperature using nothing but a layer of haze particles, absorbing and re-radiating sunlight on a daily cycle. Researchers studying the data describe the process as functioning almost like a thermostat. Haze grains soak up solar energy during Pluto's daytime, then radiate that energy away efficiently enough at night that the upper atmosphere loses heat faster than it gains it, a cycle repeating with every single rotation. Scientists are describing this as a genuinely new category of planetary climate, distinct from anything documented on any other world studied so far, including much larger, more thoroughly observed atmospheres like Saturn's moon Titan, which has its own haze but doesn't appear to rely on the same cooling mechanism to nearly the same degree. That discovery opens an obvious next question. If a small, distant world like Pluto can regulate its own sky this precisely using nothing but suspended particles, what might other hazy, poorly studied worlds scattered across the outer solar system be doing that nobody has measured yet? That question turned out to connect directly to a second mystery, one involving not Pluto alone, but its relationship with the moon orbiting closest to it. Pluto has been slowly losing atmosphere to space for billions of years, gas drifting upward past its weak gravitational pull and escaping outward. Scientists have understood that basic leak for a long time. What remained unclear for years was where all that escaping material was actually ending up. It turns out it wasn't simply dispersing into empty space. Something was catching it. Charon, Pluto's largest moon, orbits close enough that the two bodies are gravitationally locked together, each permanently showing the same face to the other. Most of Charon's surface is unremarkable water ice, gray and heavily cratered. Its poles are a striking exception. Both are stained a deep reddish-brown, visibly darker than anything else on the moon, a feature scientists suspected for years was somehow connected to material coming from Pluto, without being able to fully confirm the mechanism. The explanation turns on Charon's specific orbital tilt. Because of how the moon is oriented as it circles Pluto, its north pole spends multi-decade stretches in complete darkness, receiving no sunlight at all during that period. That makes it an efficient cold trap. Escaping gas from Pluto's thin atmosphere drifts across, freezes solid onto that permanently dark pole, and accumulates there over years. When sunlight finally returns to that region of the moon as the orbital geometry shifts, the frozen material doesn't simply melt and disappear the way you might expect. Instead, solar radiation and cosmic rays break the frozen molecules apart and reassemble the fragments into heavier, more complex reddish compounds, chemically similar to the tholins seen on Titan. That new material doesn't evaporate away. It stays locked into the surface permanently, deepening the reddish stain with each repeated cycle. Two separate worlds, one continuously shedding a small piece of its atmosphere, the other quietly capturing and chemically transforming it into color, have effectively been trading material back and forth for longer than either has had a name attached to it by anyone on Earth. Charon held one more surprise. In 2024, a team led by planetary scientist Sylvia Protopapa used Webb to examine Charon's surface composition directly and confirmed, for the first time, the presence of both carbon dioxide ice and hydrogen peroxide frozen into the moon's surface. The carbon dioxide most likely originated from material excavated by ancient impacts, dug up from beneath Charon's outer layer. The hydrogen peroxide appears to have formed gradually over long stretches of time as radiation steadily struck and rearranged the moon's water ice into a different molecular form. A moon many scientists had treated as a comparatively simple, unremarkable ice ball turned out to carry a considerably more complex chemical history than expected. Put together, here's what's actually established at this point. Pluto is cooling its own upper atmosphere using suspended haze particles in a cycle unlike anything documented elsewhere in the solar system. That same haze slowly leaks material into space where Charon's uniquely dark, cold pole captures it and converts it into permanent reddish deposits through repeated exposure to sunlight and radiation. Two frozen, distant worlds quietly exchanging material across a shared orbital dance that's been running for billions of years. But there's a further layer to Pluto's story, one that reaches beneath the visible surface entirely. New Horizons photographed features on Pluto's surface unlike anything documented anywhere else in the solar system. In a region later named Tartarus Dorsa, tall, jagged blades of frozen methane rise in long, regular rows, some reaching more than 1,500 feet in height. Much smaller versions of this same basic formation exist on Earth in certain high-altitude mountain deserts, where they rarely grow taller than a person. On Pluto, the same underlying physical process appears to have operated on a vastly larger scale, over a vastly longer stretch of time. A 2025 reanalysis of the original New Horizons dataset suggests these ice blade formations may extend across as much as 60% of Pluto's equatorial region, forming something close to a continuous jagged ring circling much of the small world. Elsewhere on the surface, not far from the heart-shaped plain, sit two enormous, isolated mountains that remain only partially explained. One rises roughly 13,000 feet. The other may reach close to 20,000 feet, with a base wide enough to rival some of the largest volcanic structures found on Earth. Both feature deep depressions at their summits, ringed by cracked, lumpy terrain closely resembling cooled lava flows, despite there being no molten rock anywhere on Pluto to produce one. If these features are what they appear to be, they're cryovolcanoes, structures that once pushed a thick, slushy mixture of water, ammonia, and methane up from somewhere beneath Pluto's frozen outer shell. That observation raises the single largest open question in this entire story. If something beneath Pluto's surface was once warm enough to push liquid material up through miles of solid ice, is that warmth still present today? Current scientific modeling suggests it's plausible that Pluto is hiding a liquid ocean roughly 100 miles beneath its icy crust, kept from freezing solid by residual heat, still radiating outward from Pluto's rocky interior. There is no direct photographic confirmation of this ocean. The evidence is inferential, built from surface patterns, cracks across it. Pluto's crust align in ways consistent with a shifting subsurface liquid layer, and that same heart-shaped plane appears to sit directly above a region where something denser than the surrounding ice seems to be exerting extra gravitational pull, as though a heavier mass were positioned beneath it. If that hidden ocean genuinely exists, it would have been sealed away from any sunlight for billions of years, sitting under enormous pressure in complete darkness, receiving only occasional replenishment through cracks in the ice above. That combination, liquid water, extreme isolation, and geological longevity, makes it one of the more scientifically intriguing possible environments in the solar system for studying the basic chemical conditions life requires, entirely disconnected from any star's direct light or warmth. There's one further piece connecting back to the haze itself. Even the faint sunlight that reaches Pluto is enough to break apart methane molecules high in its atmosphere. Those fragments don't simply vanish. They reassemble into heavier, reddish-brown organic particles that drift downward and settle onto the surface over time. Material chemically similar to this is part of a broader category of complex organic molecules some researchers believe may have rained down onto the early Earth, potentially contributing some of the raw chemical ingredients life eventually built on. On Pluto, an analogous process has apparently been running continuously for roughly 4 billion years, A slow, steady deposit of complex organic material falling onto a world that has, so far as anyone can currently tell, remained too cold for any of it to do anything more than accumulate. Pluto's demotion from planet to dwarf planet in 2006 turned out to mark the start of its most scientifically interesting period, not the end of its relevance. It sits inside the Kuiper Belt, a vast, largely unexplored region containing hundreds of thousands of icy bodies, the overwhelming majority of which have never been observed in any real detail. If one small, previously dismissed world was hiding a self-regulating atmosphere, a moon quietly capturing and transforming its escaping gas, a jagged ring of ice formations circling much of its equator, and possibly a hidden subsurface ocean, it raises a reasonable question about how much else is sitting undiscovered in that same region, waiting for the right instrument to finally take a close enough look.